Okay, so welcome to this episode now. Alright, so the camera is set up and everything is set up, so it should be pretty easy and to go. Okay, what we'll do today in this video, we'll do basics of AC circuits, as you can see here from the title. And what do you mean by that? Well, we are going to use a resistor, a capacitor, and an inductor in an AC circuit. And now I'm going to show you how you calculate the values for them inside an AC circuit. Because last video we did info about the AC source. So you should watch that one obviously before you watch this one, because we are going to use many factors of the AC source in this video, of course, because the source is a big part of it and it's got its own way to calculate. Okay, now let's get started. First, resistors in an AC circuit. Well, they are pretty self-explanatory because they were normal resistors. You use the peak value of the voltage and the peak value of the current, and then you just divide it by the resistance. And so you get the peak current or you get the peak voltage, depending on what you want to know. And as I wrote here as well, IM is the peak current in the circuit and VM is the peak voltage in the circuit. Let's go to the next one, which is inductors. Inside an inductor, the IL lags VL by 90%. And if you remember from last time, let me get a piece of paper and I'll show it to you. It's the difference between lags and leads and how it affects, because we did it inside the AC source. And basically, let's say this is yours, the sine wave, there you go. And what it means, well, if it lags, then it moves forward from the original point by 90 degrees, let's say, and it will become like that. That means it lags, it is behind. While if it's leading, then it will be somewhere around here. It will be even further back, and that will be the sine wave, and that means this is leading. Again, if you want to know more about leading and lags in a circuit, watch again the AC source circuit, because that one, it's where I explain how lag and leading works. But anyway, let me put this paper away. So let's keep going. XL is the reactance of the inductor. However, it can be used to represent the resistance of the inductor. So XL basically is the resistance inside the inductor, and it's very important to know this, because that means we can replace any components such as inductors and capacitors with their reactance values, which basically are resistors, because they are measured in ohms. And all we need to do to find this ohms value is not even the current or the voltage, it's just the angular velocity, the W, and the L, which is the inductance. That's measured in henries. And you just multiply the two of them and you get the ohm value, and that's the easiest way to discover it. If not, you can also discover it by dividing the peak voltage by the peak current to get the value. However, I don't really recommend this way of calculating, because that applies only if there is only one inductor in a circuit. And you never have a circuit with only one inductor or one capacitor. You always have a circuit with a combination of the two, or of the three with resistors as well. So that's why it's important to know to calculate it in this method, because this method here is more reliable than this one here. But anyway, so that was about inductors. So let's keep going with, there you go, I lift a bit up, capacitors. And inside the capacitor, IC leads VC by 90. So in an inductor, it lags by 90. So in an inductor, it's at this point here, and inside an capacitor, it leads by 90, so it will be at this point here. So inside of a capacitor, it will be ahead by 90 degrees, while in a inductor be behind by 90 degrees. And I know it's very confusing, because you call lagging behind when the line steps over the original position, and you call it a lead when it goes behind the original position. Well, you can't really do much about it. I find it confusing as well, and I don't really like the wording either. But this is the way, this is how you call them, and this is how you measure them. It's more about perspective, really. But we can't really do much about it. Hopefully that was recording. And sorry, you might hear my dog, because she is in my room right now and she likes to play with my pillow and blanket. But anyway, let's keep going. So yeah, the capacitor will lead IC, leads VC by 90 degrees, so it will be by 90 degrees behind. And again, it's very similar to calculate the reactance like the inductor. However, you just put 1 over WC, and so you'll find the reactance. Simple enough, isn't it? Again, it's also kind of the opposite, because this one it's a simple multiplication, while this one is just 1 over and then simple multiplication. Anyway, so yeah, so this is basically how you calculate for capacitors. And again, you apply this on peak voltage and peak current if there is only one capacitor in the circuit. But again, I do not like to apply that way of calculating. That's why I more prefer this way here, because again, it's more reliable. But anyway, let's go to the next steps, which will be, let me put this a bit up, there you go, how to find frequency by using the inductance and capacitance. And it's pretty simple, because the angular velocity, if you remember, it's also written as 2 multiplied by pi multiplied by frequency. So this is its fullest form, and because it's got frequency inside of it, we can simplify the angular velocity to this form, and then by doing so we can also easily calculate the frequency inside the inductor and inside the capacitor. And I already simplified these two forms for you, so it's easier for you to calculate. And yeah, also how to calculate the average power, also known as real power. And again, it's like calculating, it's a special way to calculate, because the average power will be equal with the peak voltage multiplied by the peak current divided by 2, and then you'll multiply that one by the cosine of the angle that of the component that you want to calculate, because some components have like 90 degrees or 110 degrees, other components might have like minus 20 or minus 30, and in special cases you might actually need to compare them, like comparing the angle between the voltage and the current, and you have to calculate the phase between them. And yeah, and also another way to write it down will also be by using the RMS. If you don't want to use the peak values, you can use the RMS values. You just multiply the peak values by 0.707, and then you multiply by the cosine of the angle again. Okay, and here is a note for you that says the ideal power or average power dissipated by a capacitor or inductor is 0 watts. So that is the ideal power. Okay, power when using different angles, and that's what the one that I meant, that you might need to know the difference between the angle of the voltage and the angle of the current. And again, angle of voltage, angle of current, and you need to apply this formula. It's really easy to do, and you'll notice it in the problems that we'll do. It's really easy. So I won't explain it too much, because it's complicated if I try to explain without showing it to you, and also you wouldn't really understand what these parallel lines are, because these parallel lines between them, it means that it reverses the sign. Instead of a plus, it will become a minus, and instead of a minus, it becomes a plus. But anyway, we'll see this when we do the problems. And again, I rewrote the formula, because we're going to use the cosine, the angle that we are going to use the angle difference that is getting from this formula. And lastly, it's the power factor. The power factor doesn't really play a big role in this one. I don't have any exercises with it to show you, because basically it's like the power average, but the power factor, it's helping you if you want to like change the component, or if you want to like put another variable and you want to get the answer very quickly. But yeah, sorry, again, I was looking at my dog, because I just can't leave her alone. She's so playful, let's say, with all my stuff, and I don't want her to like chew on any of my papers or something that she's not meant to chew. But anyway, So yeah, that's the power factor and the way to calculate it. Alright, so now that we did the introduction, and we did it quite quickly in 10 minutes, let's go to do, don't worry, there are many problems to go through, and I'm going to have many examples of how to store these formulas, to use these formulas. But so let's go to the problems. Let's start as usual with something very easy and very basic, which will be this one here. An AC source circuit that uses resistors. Well, basically it's a resistor, it's not an S at the end of it, but whatever. And this one, the AC, the alternative current, is got a peak voltage of 10 volts at a sine of the angular velocity 1 multiplied by the time. Okay, so let's start with A. What are they asking us? Find the current in the circuit. Well, okay, this should be pretty simple, because the current in the circuit, as we saw from this formula here, because it's only one component, we can simply do the peak current, it's equal with the peak voltage, no, sorry, IR, it's the peak voltage, yeah, the peak voltage is divided by the resistance, so we can write it as IR, because it's also only one current going through it, it's not splitting up in many currents, so we don't need to worry about splitting up. It's equal to VM divided by R, and that will be equal to 25 divided by 5. There you go, now she settled down. And that one will be, therefore, IR will be equal to 5 amps. So there are 5 amps going to the circuit inside the resistor. So the resistor has 5 amps inside of it. Right, let's go to B. Find the, oh, but this is not the full form, because we also need to remember to add in the sign. So that will be sine, that will be 1 multiplied by t. There is no angle difference in here yet. Why? Well, as you know, only inductors and capacitors have angle differences. Resistors will maintain the same angle. As you saw here in the definition paper that I showed you earlier, inside the capacitor, IC leads VC by 90 degrees. And so if this was a capacitor, then this I will be plus 90 degrees. And the voltage will stay the same. But we'll get there when you get the capacitors and inductors. Okay, so that was A. B, it's asking us to find the voltages at the resistor. So VR, well, of course it will be IR multiplied by R, and that one will be simply be, sorry about the writing, 5 times 5, which will be 25 volts. That's pretty simple and self-explanatory, and again it will be sine 1 times t, because again it's only one resistor, so there are many values I can go through. But anyway, then draw the graph for IR and VR. And don't worry, I won't draw it raw on the video, you know, I want to start doing it now, because I have already drawn it. So it will be easier for you. And here it is. Okay, so you should be able to, there you go. So I think I might just leave it down like this. Yeah, that's better. So you can see it here already. And a resistor is very basic, really. There isn't much change in phases, and the values here, like the 10 volts and the 2 amps, are basically the, wait a second, I'm sorry, I think I wrote down the wrong values. Yes, these are the wrong values. I shouldn't rely on the papers, should I? Okay, let's fix it quickly. Because we also have exercises very similar to this one. This is not 25, this is 10, because the peak voltage is 10, and that will be 2 amps. And this one won't be 5, because there are no 5 amps, it will simply be 2, and that will be equal with 10 volts. Alright, it's not, I'm sorry about that. I'm sorry if I confused you from like, where did I get the 25 from? It's the peak value, because like, you'll notice that in the future, like on the next resistor exercise, you're going to have a different one with a different angle, and the value will be 25 in here. So this is not, yeah, this is the paper actually. So yeah, but anyway, so yeah, the peak voltage will be 10 volts because that's the peak voltage in the source, and the peak current will be 2 amps because that's the peak current in the circuit. And there won't be any phases, all of them just start from the same angle and end at the same angle, and that is WT value. And you know, they will go positive at the 90s, 0 at the 180s, negative at the 270s, and again back to 0 at the 260. Now that you saw it, let's go to the next exercise, which will be D. And the next part of this exercise, D, simply asks us to like find IR and VR after 500 seconds. And you may wonder, why 500 seconds? Usually we work with milliseconds, but now this time, oh wait, actually you can see the other side, can you? There you go, that's nice. Anyway, and you may wonder, like, why is 500 seconds? Well, it's because the angular velocity is very, very small. Like, even 500 seconds, it won't be enough, I think. And why is it so small? Well, I wanted to put something simple, but I guess I put something too simple, and that's why it grew up to 500 seconds instead of a simple 5 milliseconds, you know. But anyway, so let's start calculating IR and VR at 500 seconds. So we'll just rewrite this first part, so that'll be 2 amps sine 1 times 500, and that will be equal with, and I don't have the answer for that one actually, so I'll need to do it on the calculator. There you go, so you can see it as well. We got 2 times sine, and that will be simply 500, no need but to put 1 times. And there you go, that will be 1.28 amps. Actually, it'd be like more like 1.29, let's put like 286 amps. And you may wonder, well, great, you know the point that the you know the S value at 5 seconds, but you don't really know where it's around this sine wave, or what angle it's around. Well, actually you know, and I think there's a formula to like convert it, but I won't bother you with the formula right now. We don't really need to use it, because the important thing in a circuit is to know the state value, because you can simply find it around here. So if you have to measure, like if you have to do this graph accurately, and then you measure this point here, you can see that 1.268, it's actually around here. It's around 80 degrees or 70 degrees. And you may wonder, well, how do you know it's around here? And how do you know it's not around here or somewhere else? Well, it's very simple, or here actually. And you got a good point. It's either 70 here, or is it like about 100 or 110 here, you know, somewhere around this area, either side. And that's how you kind of like can approximate the angle of it. But you know, it's not above 180 degrees, because if it was above 180 degrees, then it will be a negative value, it won't be a positive value. So it is either in this point or in this point. But anyway, so that was for the current, so that was for IR. So now let's do it for VR, and that one, the VR will be 10 sine 1 times 500, and that one will be equal with, so let me get the calculator out again, so 10 times sine 500, that one is equal with 6.423, so 6.423. Again, it's literally around the same area. It will be in a straight line in here, because there is no phase between them, so they are at the same angle all the time. So that would be volts for VR. And congratulations, you just did your very first, I mean, if you did it at the same time with me, you just did your very first AC circuit problem. Alright, so let's keep going with them. So that was the very first one, and that was the resistor, which was pretty easy. Now let's go to something a bit harder, which will be an inductor. that is got, very importantly, 20 henries. Well, in this circuit, now we don't have a resistance anymore. So what can we do? As shown before, we can calculate the XL value. There you go. Oh, sorry, let me put it behind. The XL value, because this XL counts as a resistor, so we can replace the inductor with the resistor XL. Alright, so let's put here an A. So the formula for the XL is X. Let me just put a bit higher. There you go. XL, it's equal with, and then that would be the W, the angular velocity, multiplied by the inductance in henries, which is L. And that will be equal with 1 multiplied by 20, and that will be equal with 20 ohms. So this inductor basically has the resistance of 20 ohms inside of it. And because we know the XL value, which is basically the resistance inside of it, we can simply find the values such as IL and VL. So B is asking us to find IL, but I wrote them shorter here because you don't really care about the way the problem is worded. You care more about the way to solve them. But anyway, so IL. So I guess I can use the voltage peak divided by the XL, so VM divided by XL, that will give us IL, because again, XL functions exactly like a resistor. Whatever resistor can do, the XL value can do the same thing. That's why we apply I think it's Kirchhoff's is the one that is the triangle rule: voltage, current, and resistance. And that's how we can apply that rule. So that would be IL equal with, so the voltage, the peak voltage is 10, and this one will be 20. By the way, I'm doing it right now, I'm not following the paper that I have the answers with. So that would be 0.5, just to make sure I don't make the same mistake of putting 25 volts instead of 5 volts. That'd be 0.5 amps. And there you go. And now we need to find the value, the voltage, which will be C. So VL, which will be equal with, and it's simply the resistance multiplied by the current, so it'll be XL times IL. And as expected, it will be equal with 10, because it will simply be 0.5 multiplied by 20, and that will be equal to 10 volts. Because again, it's basically a single resistor connected with the power source, so there isn't really much variation between these values. Oh yeah, and I almost forgot. Okay, one thing that I forget doing, and it's important, and you shouldn't forget it, and I shouldn't forget it either, is to add the sine, angular velocity multiplied by time, and then the angle at the end of it. So because this is an inductor, from the rules here, we know that it lags by 90 degrees behind VL. Okay, so let's write this down for the current. So then it will be sine bracket 1 multiplied by time minus 90 degrees. Because it lags behind, it's a minus value. Alright, so now we will XL times IL. What is it though, minus value? Yeah, it is, isn't it? Yeah. So, oh, I see what I did. Okay, I have you already can see it. It's not like you can see it. I have the graph here, and I was wondering, did I actually draw this one correctly? Did I actually put a difference of 90 degrees between the voltage and the current to be in front of the voltage? And I looked here and I saw, oh yeah, the blue line is the voltage, the purple line is the current. So yeah, I did draw it correctly. Okay, it'd be kind of embarrassing if I drew it wrong and you saw it, but anyway. So that would be 10 volts. I mean, it's not really embarrassing because at the end of the day we still learn together, don't we? Okay, and again we are going to put the sine 1 times the time, and this time we don't put the minus 90 degrees because this one stays a constant. So yeah, now let's look at the graph, because that's what the C problem requires us to do. And the graph for the inductor is this one right here. Okay, and it doesn't really matter if it starts at 0.0 or at -90 or anywhere else really. The important part here is that they have a difference of 90 degrees between them, which they do. The voltage might start at -90 degrees, but there's still a gap between them of 90 degrees because the current will start at the point of 0. If I put the voltage, or I set the voltage at point of 0, then the current will have started at point of 90 degrees here, because it will still be behind by 90 degrees. And you can see, because it's behind by 90 degrees, it actually finishes later. The frequency finishes later at the point of 360 degrees compared to the voltage that the wave finishes earlier at the point of 270 degrees. And I guess you can associate this with the lag, because it finishes at a later time than compared to the other values, which in our case will be the voltage. But anyway, this is the graph for the inductor. So yeah, hopefully you understand it. Now what we need to do, obviously after the inductor we are going to use the capacitor calculator. But remember, inductors are lacking by 90 degrees. It's lacking by 90 degrees, so it needs to be ahead of the voltage by 90 degrees always if it's an inductor. Unlike the resistor that you see next to it, which is simply having the same phase, there's no phase difference between them. There is a phase difference between in the inductor by 90 degrees for lacking I. Okay. Now let's do the next part, which is calculating their value at 500 seconds. So let's do that. And you'll notice something strange in here. So 0.5 A sine 1 times 500 plus 90. That's for the current. So that will be equal with. So let me do it quickly here. Times sine. I don't know if you see it. There you go. And with this new setup, you can't really see me calculating 500 plus 90. And that will give us minus 1.38 amps, and that's very interesting, minus 0.38 amps, and it's lower than 0.5, so we know this value is correct. Now this one is for the I. Why did I put IR? It's IL because it's an inductor. Yeah, sometimes I do mistakes when writing the problems, but anyway. So that'll be IL, and now let's do it for the voltage. We know the voltage will be 10 volts, so that'll be 10 sine 500, because 1 times 500 is 500, and there's no angle difference, so we just leave it like that. And that one will be equal with, and like the one above it, here where there's no difference in the voltage, we can just simply write it as the same answer, being 6.423 volts. And here you have something very interesting because of the phase difference. So let me just pull this one a bit higher, and this one here. Now you can't really see it, can you? Okay, I'll just leave it here. I'll leave both of them here. So what you'll notice is that the current, it's a negative value while the voltage is positive value. And what does that mean? Well, the voltage is 6.43. Because it's 6.43, I will say it's around here, around these values here, and that will be around either minus 70 or plus 70 probably. But however, the current is 90 degrees ahead of it, and then it will be around here at the negative value, at the negative so the positive will be like this, and then that's a 90, and no, it's a difference of 180 really, isn't it? Because it will either be in this one here or in this one here, because it's a negative value. But you get the idea, like it matches around. So yeah, while the voltage V is positive and the current is negative, it shows that there is a difference in phase between them. And of course that difference was made by the 90 degrees added in. Alright, so that was simple, that was the inductor. Now let's go to the next one, which again it will be the... Actually, let me like set up the camera a bit better, and let's do the capacitor, and then I'll turn on the flashlight for it, and I will also drink some water, and I'll better set up the camera after this one. Now we have a capacitor instead of an inductor, and this capacitor's got 2 farads, 2F. So again, we need to find the resistance, the X value. We need to find the current going through it, you need to find the voltage going through it, and you need to draw it on a graph and find their values after 500 seconds. Alright, so formula for the XC will be equal with 1 over WC, therefore XC will be equal with 1 over 2 multiplied by 1. Therefore XC will be equal with simply 0.5, wasn't it? Yeah. Alright. Ohms. There you go. Now we need to find the IC. And IC, it's basically the current in the circuit. It's a resistance of 0.5. So, and it's a voltage of 10. So the current will basically be equal with 10 divided by 0.5. Therefore IC will be equal with 20 amps. So there are 20 amps going through it. Sorry about that. Okay, and now we need to calculate the VC value. VC will be equal with, and we just do the current multiplied by the resistance. That will be 20 times 0.5, and that will be equal with 10 volts, the maximum value. And then actually let's just put the full form of them. So be 20 amps sine 1 times t plus, no, this one will be minus, yeah, minus 90 degrees, because IC leads VC by 90 degrees in a capacitor. Okay, and then the voltage will basically stay the same, there won't be no difference. The reason why only one of them get the plus or minus 90 degrees is because if both of them have the plus 90 degrees or the minus 90 degrees, then there will be no phase difference. The only difference will be that they start at the point of 90 degrees instead of starting at the point of 0. But anyway, next step is to draw the graph, which I did in here. Very similar to the inductor graph. Just give me a second to, there you go. Very similar to the inductor graph. Simply the current goes a lot higher. Instead of going to 5 amps, it goes all the way to 20 amps, and the voltage here will be 10 amps, and it will lead by 90 degrees, so the current will be behind the voltage by 90 degrees. So it starts at minus 90 while the voltage starts at 0. And now we need to calculate the value of IR and VR at 500 seconds. As asked here in problem D. I didn't need to change the camera, and let's put it IP, and this one will be C, and this one will be E. Okay, so IC is equal with 20 sine 1 times the time, which is 500, minus 90 degrees, and that one will be equal with, so that will be 20 times sine 500 minus 90, that will be equal with 15.32 amps. So 15.32 amps at the time of 500 seconds. and then VC will be equal with 10 sine 500, and again it will be the same value as before. It will be of the voltage. I get the resistor, and I don't have it written down on my other piece of paper, so I just flip this one out. 6.423. okay, you go with 6.423 volts. So when it comes to volts, it will be somewhere around here at the 6.3. Again, it will be 70, or it will be 110, and then for the current's around 15.32, so it will be around this area here, and this one will be about this way here, or this one here, and that will be around like either minus 40 maybe and plus 40 degrees. All right, so that was the simple circuits, the circuits that have only one component in them. And on the next part of the video, we are going to do basically the same thing again, circuits that have only one component in them, but this time they'll have a different angle. For example, this one has plus 60 degrees inside of it. All right, I will like pause here, and I'll turn on the flashlight, and I'll better set up the camera. Okay, so there we go, we are back now. Sorry, I had a sip of water. So yeah, now let's do it with an angle, and this is an angle of 60 degrees if it doesn't clear, and it's got an angular velocity this time with 377. So let's make it a bit more complicated. Let's like add to it, you know. We start with very basic, very simple numbers, and now let's add a few numbers to them. And if the peak voltage now will be 25 volts, as you saw from the mistake before. And again, I'm sorry, but my dog, I don't know what she wants now, but yeah, let's keep going. So this is a resistor, and again we need to find the IR, we need to find the VR, we need to graph the values of IR and VR to show it to you. And what is the value of IR and VR after 5 seconds, and the value of 5 seconds. Alright, so let's get started. Let me get I also changed the camera angle so you can see more of the page instead of less of it. Okay, so let me do this. There we go. And your little dog. She's a Shih Tzu, by the way, but yeah, I thought it would be like nicer and more chill and sleeping a lot more, but apparently not. Or maybe she's just different from others. Anyway, so the formula for current, as you know, is basically I over IM over VM, because we use the peak values, divided by the resistance R. Therefore, IM, it's equal with 25 divided by 5, and that will be equal with 5 amps. Now let's do the same one, but this time we'll do it for VR, which is the voltage inside the resistor. So VR it's equal with, and to calculate it, we simply do VM divided by IM, and then therefore VR will be equal with, oh my god, I'm sorry, she's distracting me. I'll pause here, I'll be back in a minute. Okay, I'm back. She does an amazing job of getting my attention. Alright, I just let her out. Maybe she just wanted to go out, stretch her legs. Probably got bored of like staying in my room. Anyway, so sorry about this mistake. So that would be basically the resistance times the current. So that would be R times the peak current IM, because there's only one resistor inside, and that will be equal with 5 times 5, and that will be equal with simply 25 volts. Again, the peak value of voltage, it's going through the resistor. Alright, so that was for B. Now C, it's asking us to see the graph, which I have already made, and it's right here. Give me a second, and there you go. This one is the graph for the resistor, and it's got an angle of plus 60 degrees. And actually I should write this down as well. Okay, for the current, and that will be sine 377 multiplied by the time plus 60 degrees, and then for the voltage is the same because this is a resistor, there is no phase difference between them, so that'll be 377 times t plus 60 degrees. Okay, and here is the graph, and basically because it's plus, so it's like adding to the value. I wrote it down at the minus value, minus 6 degrees, so it starts at the minus 60 degrees and it will go like that. And the peak values, you know, like the value of 5 amps and 25 amps, it's about around the 30 degrees going up, because minus 60 degrees plus 90 degrees, that will give you 30 degrees, and we know that at 90 degrees that will be the peak positive, and at 270, or in our case it's going to be 210, after 180 degrees it will be the peak negative. Alright, so this is the graph for the resistor. Pretty simple, both of them, the voltage and the current, are in phase, so there is no angle difference between them. But again, because it's simple, that doesn't mean it's everything done. Now we need to go to the next parts, which will be an inductor and a capacitor like the previous one. Oh no, wait. Also, we need to calculate the, what is it called, the time constant, like the value of current, the value of voltage after 5 seconds. So let's do that now. So Im will be equal with 5 amps sine 377 times 5 plus 60 degrees. That one will be equal with, so 5 times sine 377 times 5 plus 60, that one will be equal with 2.87, let's say, so 2.87 amps. Now let's do it for the voltage, which will be the 25 volts. So Vm, actually I don't even know if I should put like M values. I think I should just put R values really, because the resistor, that'll be 25 volts sine 377 multiplied by 5 plus 60 degrees. That one will be equal with, so we replace 5 by 25, that'll be 14.33, 14.34, let's see, volts. Alright, and again, if you want, we can look at this one. So it's like 14.3 and 2.7, so it will be somewhere around this area here, or either this or this here, so it'd be around minus 40 probably, and minus 80, yeah, either minus 40 or positive 40. Okay, so that was for the resistor. Now let's go to the next one, which, oh sorry, I need the other page, because this one is finished. We did all the exercises on this one. Let's go for the next one, which is this one. Is it? Yeah, it is. Is this one here. There you go. Now you can already see the inductor and the capacitor. Again, don't worry about it. Like, if you don't understand the writing here, they still have the same values. You know, it still has the same source. The only difference is that the inductance, the inductance here, it's 0.05 henries. And again, it's asking us to find the IL and VL after 5 seconds. Alright. So, but first we start with A, which is find the XL value. And we know that XL is simply equal with the angular velocity multiplied by the inductance L. Therefore, XL will be equal with 377 multiplied by 0.05. And I actually have the answers for these problems right here in front of me. That one will be equal with 18.85 ohms. So that will be equal with 18.85 ohms. So that's the resistance that replaces it. Okay, now let's find the current, IL. So IL will simply be equal with, and we can do the voltage peak Vm divided by the XL, which in our case is 18.85. So then IL will be equal with 25 divided by 18.85, and that one will be equal with 1.33 amps. Alright, now let's go to C, which is VL, and VL will simply be equal with XL multiplied by IL, and as you already know, this one will simply be 1.33 multiplied by 18.85, and it will simply give us the answer of 25 volts. Alright, D is drawing the graph, so let me show you the graph for it. And it's this one here, and I almost forgot the most important part, which was to add them. So that'll be sine 377 multiplied by time plus 60 degrees, and then this one here, I think it will be, let's see, so for the inductor it's a minus, this one it's like, so it'll be a plus 90 degrees. Alright, so that would be plus 90 degrees. So that's how you calculate the current. We add the 90 degrees because, as you can see from this paper here with the rules, inside an inductor lags IL lags VL by 90 degrees. So we need to put plus 90 degrees. So VL V will be smaller because V will simply be sine 377 times T plus 60. So simpler. Okay, now let's calculate the values of IL and VL after 5 seconds. Alright, they should be, so IL will be equal with, so we just rewrite this one here, 1.33 amps times 377 times 5 plus 60 plus 90 is like 150 degrees, and that one will be equal with, so let's do it here, 1.33 times sine of 377 times 5 plus 150, that one will be equal with minus 1.09, let's say, so minus 1.09 amps. So that is the ampage. Now let's find the voltage. So VL, inside the VL it will be 25 volts sine 377, I forgot to put the sign here, sine 377 times the time, which is 5 plus, and this is simply 60 degrees because we need to have a difference between the two of them by 90 degrees. So that one will be equal with 25 times sine 377 times 5 plus 60. Okay, and that one will simply be 14.34. Actually, we did it before with the resistor. Yeah, we can see that our voltages on these ones are the same basically because of the resistance calculation, because the voltage doesn't really change. Like all of them will have the same voltage of 25 volts inside of them. The only thing that changes is the current really. But anyway, and you can already see the difference between them because one of them is positive while the other one is negative. So you can already see how the 90 degrees it's affecting those two answers, the phase between the current and the voltage. Alright, now let's go to the next one. So this one uses a capacitor. So let's first find the x value of the capacitor. So xc will be equal with 1 over W multiplied by the capacitance. Therefore xc will be equal with 377, 1 over 377 multiplied by 50 micro, which is basically 10 to the power of minus 6. And that will be equal to, and I have the answer here, that's 53 volts, surprisingly enough. No, 53 ohms. So there are 53 ohms inside this capacitor. Alright, now let's calculate the current. So IC will be equal with the peak voltage Vm divided by the resistance, which is 53 ohms. but that's set as XC. Therefore, IC is equal with 25 divided by 53, and that one will be equal with 0.4247 amps. And you can already see the current in here in the capacitor, it's already a lot lower than the current in the inductor. However, they are still different values, like one of them it's 0.05 hertz, while the other one it's 50 microfarads. So there's a big gap between them anyway. So it makes sense, like one of them has I'm sorry about my voice, I'm losing my voice for some reason, has more resistance than the other. But anyway, so now let me show you the graph. And here is the graph, is this one here for the capacitance. Again, plus 60, and this one is minus 150 because it's a difference of 90 degrees between them. So let me write down quickly as well. So this one will be a lead, so that will be minus 90 degrees, so that will be sine 377 times the time plus 60 degrees minus 90 degrees. Oh, and I forgot to do it for the voltage as well, but we already know what the answer will be. It will basically be IC times XC, and then that one will be equal with 0.747 multiplied by 53. That will be equal with 25 volts, and the full form of it is sine of 377 times the time plus 60 degrees, because it will not change, only the current changes. Alright, and as you can see there, it's a difference of 90 degrees between them. The current starts before the voltage, so it's got the lead of 90 degrees, and it's so big because I can't simply just make an extremely small line to represent the 0.47, because you don't even notice the wave of it. That's why it's bigger than it's supposed to. And there's the 25, and that's the voltage simply. And you can see the voltage will be done, will reach its full wave later by 90 degrees compared to the current. Alright, now let's calculate it with the time. So now for E, we'll simply have to rewrite it as IC, it's equal with 0.47 sine of 377 multiplied by the time plus 60 degrees minus 90 degrees. That will be equal with 0.47 times sine 377 times the time, which is 5 seconds, times 5 minus 30, because minus 90 plus 60, that will give us minus 30. That one will be equal with, as you can see here, 0.39, let's say. Now let's say 0.385. Alright, and the voltage stays the same basically, because VC is equal with 25 volts sine of 377 times 5 plus 60. There is no change in it, so it will still be equal with 14.34 volts, and this one was amps. Alright, and these are our answers. Okay, I will again take a break so I can have some more water, because my throat is really dry after all this talking, and we still haven't finished it. Like, now you understand how to calculate the basics. You also understand how to calculate it if there is a different angle, like if there is an angle of plus 60 degrees inside the source. And also you learn how to calculate it, very importantly, with all three types. You learn how to calculate with a resistor, with an inductor, and with a capacitor. The three components that we also learn in DC as well. But before I pause, let me also show you this bit of theory that I forgot to show you at the beginning. And it's not very important because we already covered a little bit. But basically I wanted to show you how frequency affects inductors and capacitors. Basically in an inductor, if the frequency is 0, it acts as a short circuit, so all the current will go through it without any problem, because the frequency is 0, so it's very high frequency, no, a very low frequency. and at high frequency, it is depending on the circuit what high frequency means, then the inductor will act as an open circuit actually. So at low frequency, a lot of current going through. At high frequency, no current is going through. And again, this is the formula on how to calculate the frequency inside an inductor. And now with the capacitor, it's the perfect opposite of the inductor. At low frequency, it's acting as an open circuit, so there is no current going through it. However, at high frequency, it's working as an open circuit with all the current going through. And again, there's the formula for it. We won't really care too much about frequencies right now. I mean, yes, we'll do a few problems with frequencies and how to determine frequencies and how to manipulate frequencies. However, the frequency it's more important for passive filters than for AC circuits in general. They are also important because it determines the X value, the reductance value as well in the angular peak. So yeah, it plays a role in there, but the idea that low frequencies act as a short circuit and high frequencies as an open circuit inside an inductor and vice versa for the capacitor, that is more of a factor that comes into play when working with filters, because the purpose of a filter is to stop some frequencies in, if you want to say it like that way. So you can actually make filters with inductors and capacitors where one path is closed inside an inductor because there will be no current going through it. So when it's high frequency, so one path is closed while the other one is open for C when it's a high frequency to go through. However, it can also be the opposite, when it's very low frequency, the path with the capacitor is closed while the path with the inductor is opened. I mean, it's only one way to look at it, but I think it's like a good example. And again, don't worry too much about it. I showed you more as a trivia. We are going to look more into it, more into frequencies and more into, in frequencies in general with filters and as we advance inside AC circuits. And also, I'm sorry if sometimes I do mistakes with AC circuits because they didn't teach us AC circuits while I was at university. We actually did only DC circuits and we didn't even finish the DC circuits properly because we didn't even do inductors and capacitors. So everything you see in these videos is new to me as well, and I try my best to understand them from the resources that I have, which is just mainly books really. I don't really rely on YouTube videos because I don't want to complain about them, but most YouTube videos, they just explain the basics, like a very simple circuit like the one that I showed you, and that's it in like a few minutes, while I want to explore more complex stuff, like more stuff that has more variables such as the angle and what if there are more components and what if you want to determine the value at a certain time and etc. But anyway, I really need to drink some water, so I'll pause here and we'll go to the next exercise after the pause if I can. Yeah, there you go. Alright, so I let my dog back in my room and I took a break, I drank water, so I should be okay with my voice for the next part of the video. Alright, so let's do now a bit of a fun exercise, which is determine the type of component, if it's RL or no, if I said RL, if it's a resistor, an inductor or a capacitor, with angles, by using the angles. Find that component, resistance, inductor or capacitor, and calculate the X reductance value and inductance / or capacitance. Alright, so let me actually set up my page with the answer for this one. Let me actually clean the table a little bit. Sorry about that. I'm not always the most prepared. Most of the time I try to be, but not always. So there I have it. Alright, now let's start with the first one. So the first one, it's got the same angle, it's got plus 50 in both sides, and also it's got 80 volts peak and it's got 20 amps peak. So let's think about it. What component can that be? Well, it's got the same angle, and a component that is got the same angle, let me like get it out here. A component that doesn't have a difference in angles, it's a resistor. There's no difference between the current and the voltage, so this one must be a resistor. And if it's a resistor, then we can simply apply the formula voltage peak divided by the current peak, which it will be equal with 80 divided by 20, and that one will simply be equal with 4 ohms. And there you go. Now let's go to B. And let's look at B. Now B is got 500 peak voltage and 220 degrees, and I it's equal with minus 70 degrees. So that is a difference. Because those two values are different, that means for sure they are not a resistor. Well, how do you calculate this? Like, how do you calculate the difference? Do you do like 20 minus 70, or do you do 70 minus 20? Well, if you think about it this way, then yeah, it will give you the same value, isn't it? Nah, not really, because either to give you minus 10 degrees or to give you plus 90 degrees. And it's very important for you to know if it's a positive or a negative 90 degrees, because again, the whole thing about inductors and capacitors is that one of them it's plus 90 degrees and the other one is minus 90 degrees, so you can't really like intermediate them. So a formula that I'm using, and I didn't show you earlier in like the preview, it's I minus V, it's equal with component. There you go. And basically we do the current, which is this one here, minus 70, and we take it away by the voltage, which is 30 in our case. So we do minus 70 minus 20, because plus with minus that gives you a minus, and that will be equal to minus 90 degrees. And what is a minus 90 degrees? Well, of course, it's an inductor, because it lags. So that would be an inductor. There you go. Minus 90 degrees, it's an inductor. And let's calculate the value of it. So XL will be equal with Vm over Im, and that one will be equal with 100 ohms. I do it this way because it's easier, you know. We can also determine the value. We can also determine the volume of the inductor actually, because we can also do 100 divided by the W, because the formula of the inductor, you know, it's like the angular velocity multiplied by the L, by the inductance. Well, now we can do it the opposite way, and that would be 100 divided by 377, and that will be equal to 0.27 hertz. And there you go. By simply determining one value, we can also determine the other two value inside the circuit. But this minus 90, this one is for the volts, so volts. Because usually for an inductor, minus 90, that means that it no, it actually, yeah, it's correct, it's for the current, never mind. As you can see here in the graph, it lags behind by 90 degrees, so yeah, there is a difference of 90 degrees because the current will be ahead of the voltage. Let's go to the next one, which is C. Hopefully I don't get them mistaken, like hopefully I don't think I did. I don't think I mistaken them. I don't think this one is a positive and the next one will be a negative or something like that. Hopefully I didn't. If I did, then I'm sorry. Maybe it's like the opposite, instead of an inductor, maybe this is a capacitor. But I don't think I did a mistake in here. So, okay, so that'll be the next one for C. This one will be the voltage will have a positive 40 and the current will have a positive 110. So again, we do the current that says a positive minus the voltage, that's like 20. No, that's like 40. And then that one will be equal with minus 150. Is it though? So plus 20. No, that's actually Let me think about this one for a second, because in my notes I put minus 90 degrees and it's obviously not 90 degrees. So I'm sorry about this. This one is supposed to be 130, not 110, and then take away by 40, and then that one give me 90 degrees. Sorry, I guess I wrote them in a rush and I didn't do this calculation correctly. Anyway, so it's supposed to be 90 degrees. That means it's a capacitor. It's a capacitor. Let's now find the x value, which will be simply be voltage peak divided by Im. To find the ohms, you don't even really need to find the you can just use the peak voltage and peak current. Really, you don't really need to do it much. But this one it's 100 because it's like 500 divided by 5. This one will be 100 divided by 1, and that will be equal with 100 ohms, so there's 100 ohms in it again. And then C, the capacitance, will be equal with, and the formula for it is usually 1 over WC. Therefore, for C will be equal with 1 over the angular velocity, which is 157. It's just a random number times 100. If you want, like, how do I come up with these numbers for the angular velocity? To be honest, sometimes I just hit the random number generator, and if it looks okay, if it looks like if it's in the hundreds, then I'll choose that one. That's why I keep using 377 and 157. Those ones are the lucky ones. But anyway, so times 100, and that one will simply be 63.7 microfarads. Extremely small capacitor. Alright, now let's go to D. This one is plus 20 and this one is plus 110. However, there's a cosine in here, and this is not okay. We need to have both of them as sines. So from the previous video on the AC sources, I also showed you a few shortcuts that we are going to use here as well. And to convert a cosine to a sine, you simply need to either subtract or add 90 degrees to it. And I chose to add 90 degrees to it, so we can write as 25 cos Wt plus 20 equal with 25 sine Wt plus 20 plus 90. Alright, so this one actually will be equal with 25 sine Wt plus 110. And there we have it, 110 for the resistance, no, not resistance, for this value. So 110 and 110, that means there is no difference in the angle, which means that they are both a resistor. So we can also write down, so 110 minus 110, it's equal to 0, therefore is a resistor. And the resistance will simply be R over Vm divided by Im, and that will be equal with 25 divided by 5, and that will be equal with 5 ohms. And there we go. These are the full values. Yeah, the full solutions. Alright, and don't worry, we didn't finish yet. There is still lots that we need to go through. And I don't know, you may feel like, oh yes, we are going to go through more, so we're going to see more ways to use these formulas, or may I go like, oh no, we need to go through more of them. Why doesn't this guy just stop talking and just upload the normal 1 hour video like everybody? Well, I wish I could do that, to be honest. Actually, I can't do that, but I don't know, I want to do it properly. I want to like explain as much as I can and learn for myself as much as I can. Okay, this is the average power, but I want to do the one with the angles. Is this one the one with the... yeah, this is the one with the frequencies. There you go. Alright, so let's go to the next exercises, which basically are how to calculate the reactance with frequencies. And basically in one, it basically can use frequency to determine the reactance, which is the resistance. So reactance is actually really cool. It's not like a normal resistor. With reactance, you can also manipulate the frequency. Not really manipulate. Like with the reactance, you can also calculate the frequency inside the circuit. Alright, so here let's say we just don't know the frequency, you know, but we do know the value of L, which is 100 millihertz, and we also know the XL value, the reductance value, which is 2k ohms. And what we need to know is what frequency is required to get this reductance. And this is actually a pretty simple problem with a fast solution. First off, the angular velocity that's usually used in here is equal with 2 pi times frequency. Therefore, XL is equal with, because it's equal with W times L, therefore we replace this W with we simplify it. No, actually it's not simple. We expanded, let's say, yeah, we expanded to its original form. Therefore, XL is equal with 2 pi multiplied by the frequency multiplied by the L, the inductance. Okay, so XL will be equal then with 2000, because we already know this value of 2000, which is also equal with the 2 pi times L times the frequency. So all of three of them are equal to each other. So now we just need to move everything from this side to this side, and then we are going to have only frequency left. Alright, so let's keep going then. And that one will be like 2000, it's equal with 2 pi times 100 times the 10 of minus 3, because that's milli, times the frequency. And that one, therefore, 2000 ohms will be equal with 0.628 and multiplied by the frequency. And my dog just found herself a new toy to play with while I record. Alright, let's go quickly through this. Okay, so then therefore F, the frequency will be equal with 2000 divided by 0.628, which is the value here multiplied by the frequency. So therefore it's somewhere around 3.2k hertz. So the frequency needs to be 3.2k hertz to get an inductance, no, not inductance, to get this X value reductance of 2k ohms. Yeah, the second is to have 3.2k hertz. Alright, I'll pause and then until my dog and let my dog finish whatever it has to do. Okay, hopefully you won't hear her, but she found herself a new toy, and yeah, if I try to take it away from her, she just won't leave me alone. She'll like chase me and like yonder at me and everything. Oh my god, she knows how to get her way. She knows how to annoy me and like until I give back whatever she was playing with. And let's see here. So next example is like, at what frequency will the inductor of 10 millihertz have the same reactance as a capacitor of 0.1 microfarads? So basically, at what frequency XL will be equal with XC? At what frequency these two will be equal? And you may wonder like, well, can you actually calculate something like this? And the answer is yes, and it's actually very easy to calculate, because 2 pi FL, you got 2 times F times L, that's the formula for the reactance here, and then the formula for the reactance of the capacitor is 1 over 2 pi times F times C. And we can rearrange these two formulas to get only one formula, which will be F squared equal with 1 over 4 pi squared L times C. A very simple formula. And again, like by just writing down the formula and by just simplifying them, like just opening them up to their core values, you can kind of like always find the answer to it. and because we know the inductance and the capacitance, we can easily calculate. We can easily rewrite this formula and find the frequency. So F will be equal with 1 over 2 pi square root of LC, because we like square root this value here at the bottom with the square root of from F, and that one will be equal with 1 over 2 pi times square root of 10 times 10 to the minus 3 multiplied by 0.1 times 10 to the minus 6, and all of that will be equal with 5.032 k hertz. So we already found like what frequency we need to get XL and CCL to have the same value at when XC it's equal when the reactance of the capacitor when the capacitance is 0.1 microfarads and the inductance is 100 millihertz. And now my dog runs outside because she changes her mind every single second. Okay, so, and again, you can do this, you can apply this formula with any value of the capacitor and the inductor, and you'll get like the ideal frequency for it. But anyway, so yeah, our answer is 5k. I said, just give me a second to drink some water. Oh, okay, so that's the frequency that we need to get both to have both of them equal the same reactance. Alright, and again, this one is just very simple and very fast. We didn't even need to draw the circuit diagram or anything like that to like find the answer or calculate, or we didn't even need the voltage or the current to find the answer for it. We simply need the component values. Alright, now on the other side we have powers.